Let's have a look at question 1 in this video. So we have two towns that want to collect garbage and they want to investigate the amount of waste produced by the inhabitants. Okay, it may be assumed that the amounts of waste are normally distributed with the means of mean A and mean B in the respective towns, and they have standard deviations as well. Now, in every town we collect a simple random sample, and we have 10 households, so the number of observations in each group is 10. We have the sample averages and the sample standard deviations, the sample variances actually, because the standard deviation to the power of 2 for group A and for group B. Now we want to test whether the average amounts of waste are the same, but for that we want to know first whether the variances differ. For that we run the test at this significance level of 10%. What do we do with the hypothesis? So we have the data over here. Let's understand the reason we're doing this test to begin with. We have the variances in every group, and we're testing now the variances, whether they're similar or not. What we also need to know is that the number of observations per group is the same. So we have number of observations in group B, 10 households, number of observations in group A, 10 households as well. This is the foundation for the test that we're going to do afterwards. Whenever we want to test a difference between means, we're going to run a t-test, assuming that the means are independent. And in this case, we're having two independent groups, two independent towns. So we're going to have a difference between means, but we have two requirements, or better said, we have two types of tests. Either we have equal variances or we have unequal variances. So the reason we're doing this test on variances right now is to figure out which one of these we're going to have to run the test on difference in means in the next question. So with that said, we're running this test on variances. This is the hypothesis that the variance of these waste products in town A is the same as in town B, or they differ from each other. And to run this test, let me just zoom out first. To run this test, we're going to run an F-test where we take the ratios of the variances from the samples. Because the sample data, remember, it's always an estimate of the population data. This variance for group B and this variance for group A is an estimate of the variance in the entire town. So what we're going to do, we're going to run an F-test where we take the ratio of the larger variance to the smaller variance. We're going to take the sample variance that's larger relative to the sample sample variance that's smaller. Now, why do we take a ratio of the variances? Because this is the intuition. If they are close to each other, and mathematically that means that this ratio is close to 1. So if they are close to each other, then what we can say is that the larger variance is similar to the smaller variance. So they are almost equal. Remember, this is statistics. We cannot give certainty like it is equal. It just has to be similar enough. If we have this evidence, then we know we can assume equal variances. If we're going to prove it wrong, that they differ significantly, we're going to assume unequal variances. That's the intuition. So let's work out the math to see what we get. What is the larger variance? Is this one, 3050. So we're going to have the ratio between 3050 relative to the smaller variance, which is 1225, 1225. That F value is going to be equal to 2.49. So 2.49. Now what matters here is to understand how we find out the critical value. The F critical value has 2 degrees of freedom. So this F distribution is slightly different than the other ones because it has 2 degrees of freedom that we must take into account. We're having a two-sided test, and on a test on variances, we consider the significance level is going to be 0.10 divided by 2. So we're spreading it on 2 sides. And the degrees of freedom are going to be the number of observations in the group with the larger variance. And in the group with the larger variance, we have 10 observations because we have 10 observations in each of them. So it's going to be that number minus 1. So it's 10 minus 1 in the numerator. And the same logic goes for the denominator. The number of observation in the group with a smaller variance, they also have 10 observations minus 1. So it's going to be the F critical value with a 5% significance level. 5% significance level with degrees of freedom 9 and 9. And we compare this, or actually we look for it in the table, and that's going to be equal to 3.18. And with these two numbers in mind, we're going to see the relationship between them. Is our value in the rejection region or not? Now we have here the, let me draw that better. We have here the, yeah, not good, but anyway, we have here the F distribution, and we know that the critical value is going to be 3.18, so it's somewhere over there. Now this is going to be our rejection region, values at least equal to 3.18. Our value is 2.49, so it's somewhere over here. We can see that it's not in the rejection region, so we're going to give the appropriate conclusion, which is that we do not reject H0. We do not reject H0. So what does that mean? We don't have enough evidence to claim that the variances differ. So we assume that the variances don't differ significantly. Variances don't differ significantly. If they don't differ significantly, then we assume them to be the same. We assume them to be equal, which is what we're going to use for our next test to test the differences between means. Hope this makes sense, and we are done.